Well, welcome to another dose of science. And the question always is, do we have a small dose or do we have a big dose? Well, today we have a pretty big dose of science for you with our special guest, Professor Audrey Moores, my colleague here in McGill Chemistry Department. And joining us also are regulars Ada McLean and Jonathan Jerry. The topic today, green chemistry. Of course, I guess we have to start with talking about what that is, because usually the word chemistry is not preceded by green. In many people's minds, it's preceded by toxic or poisonous or dangerous, toxic chemicals, dangerous chemicals. So what is green chemistry? All right, we asked Professor Moores to join us because her research focuses on green chemistry. So let's get the ball rolling by just trying to explain what green means in connection with chemistry.
Yeah, so this is a great question. Thanks a lot, Joe, for inviting me onto your show. So green chemistry is really a movement that started within the chemistry community about 25 years ago. And over the years, actually, now it's changed its name. Now we refer to it more like sustainable chemistry. It's a little bit different, but it encompasses green chemistry pretty well. And the concept behind it is this idea that if we're going to do research on chemistry, let's try to do it with in mind two aspects that are really important. We want to do it keeping in mind that we don't want to harm the environment and that we don't want to harm the health of people. So it's really looking at products that are coming from chemistry or processes that are using chemistry. But we're trying to envisage better ways to do it so that the impact around us and on our own health is a little bit better.
This movement really started full impact in the 1990s. And let's face it, before that, we weren't all that interested in what happened to chemicals after they were used, after they were dispensed with, because there were problems to solve. And the question was, how do you solve this problem? We needed new materials, so you go into the lab, you design chemical ways to arrive at them. So we had plastics, we had antibiotics, we had pesticides, we had fertilizers, all of which emerged because they were needed and they made our life better. DuPont, of course, told us better living through chemistry. And then, of course, we started to see that some of these chemicals ended up in places where we didn't want. Rachel Carson in 1962 raised our awareness with Silent Spring that, birds perhaps were having a problem because they were exposed to DDT. Then we had Love Canal. Then we had the thalidomide issue. We had the Bhopal explosion. So our thoughts started to turn towards how do we do things more cleanly? How do we make things better? So Audrey, I know that you're focused on green chemistry, but on a very, very specific aspect of green chemistry, because you've become interested in a chemical called chitin, which makes up many fungi, and it also makes up the shells of crabs and lobsters and shrimp. And chitin, I think, is the second most widely available chemical in the world after cellulose. So the question is, what do we do with it? So describe to us your research and where chitin is going.
Yeah, so this, related to green chemistry, I'll start with this to make the connection. We're trying to find ways that we can lower the impact of humans on the environment. And one of the places where we have a big impact is the waste that we generate. And we consume a lot of crustaceans. I don't know about you, Joe, but I love a good lobster. It's really delicious. And but this generates a lot of crustacean waste that we don't always know what to do with. And this is really a significant problem in Canada, in particular on the east coast of Quebec and the Maritimes. They have to deal with this. And I can tell you there's a lot of producers that are calling me and saying, Audrey, we need to do something useful with all this crustacean waste. So the idea became, can we use this material? Because it's a beautiful material, as you said. It contains a lot of really interesting molecules that we can use, and try to turn it into something useful. turns out that there are lots of things that we can do with chitin, in particular, turn it into a molecule called chitosan, which is another form of, it's a small modification of its structure. Really interesting. They're antibacterial. They can be useful to make sutures, or to be used in biomedical devices. They're applied to water treatment. They're applied as fertilizers. So people have applications for them. But the bigger problem is, how do we transform the crustacean shell into chitin and then chitin into chitosan? These processes are so wasteful right now that we stopped producing them in Canada altogether, despite the fact that we have a huge amount that is produced every year. So what do? We just dispose of this waste, in the best way we can. But the more it goes, the more people have the pressure to do something useful with them, because the governments are not letting them put this anywhere anymore. So that's where we come in. So what we did is we looked at the process as it exists. It's a process that uses a lot of water, actually, a lot of chemicals that are corrosive, and we've transformed it into a process that was without the water. And what this does is it means that the handling of the chemical is much safer, and we generate far less water that will go back to the environment, and this water is less toxic, essentially. So it limits a lot the price that you need to put in the process to clean it up after the fact.
So you mean you're using basically a solid state method?
Exactly. So just to give you a quick idea of what this is. So if you take a crustacean shell, again, if you eat lobster, you know, like me, that when you want to try to get to the flesh of it and eat it, you have to play with the carapace, and the carapace is this nice feel to it that makes it feel a bit like plastic. And that is because inside the carapace you have chitin. Chitin is a polymer, and it means it's very similar to plastics that we know around us. So what you need to do is you need to take this out of the rest of the carapace. The rest of the carapace is made of minerals, like calcium carbonate, things similar to eggshell, essentially, and a bit of proteins as well. So what you need to do is you need to first take the carapace, grind it, and then extract the chitin from it. And then once you have the chitin, which is about between 15 and 30% of the weight of the carapace, then once you have this, you need to turn it into chitosan by a small chemical transformation. And since you does not allow me to name it, because it's too chemistry oriented, I won't do that. But it's just changing a tiny little structure on the top of the polymer itself. And that's it. But both these processes, the demineralization, remove of the mineral, removing the protein, and transforming chitin to chitosan, all of these processes require a lot of acids and bases and water. And what we do is we can transform all of this into the solid phase, which generates far less waste after the fact.
Of course, one of the most important things about green chemistry is using renewable resources, but the other aspect is what to do with it after it has served its purpose. Exactly. So chitosan is biodegradable, right? I mean, this is one of the positive features. So what happens to the material that you've made after it has served its purpose?
Yeah, so that's a great point. So I think this really goes into thinking about the products that we have around us. And I like the reference you made to the need that we have to chemicals around us, because it serves a purpose for us. And there is a lot of molecules around us that are really important, and plastics are one of them. Plastics are really beautiful molecules. We can make them from oil, as I'm sure you've discussed on the show many times. We can make them from biomass. And when we do this, there are trade-offs to doing one versus the other. The oil is actually often more environmentally friendly to take as a starting material, because the process to making the plastic is more environmentally friendly. And also growing the plants or growing the biomass in the first place often comes with environmental costs as well that we need to take into consideration. So if you want to make a piece of plastic to put in your car, for instance, that's going to be there for decades, then I would say in a lot of cases, the plastic from oil makes more sense because that's fine. But we have issues with plastics that end up in the environment. So some plastics, either the single-use plastics, like the little plastic bottle that you use for water, or the straw, or the cup that you have from the coffee shop, these have a higher chance proportionally to end up in the environment and to do so in large proportion. So for those, we need to make sure that we can think about ways that they will degrade when they go to the environment, because it is an environmental burden if it ends up in the ocean. Another one we don't think of is actually fisheries. So when you go into the ocean and you collect the plastics that are in the sea, people have done this analysis. And in fact, the first source of plastics that you have there is actually plastics that's coming from fishery activities. So old buoys, fish nets that are broken, parts of boats, whatever. And these degrade over time and end up into microplastics that can then be damaging for the fauna inside the sea. So what we're trying to do is to figure out how we can use our chitosan that we made to make a bioplastic. And this bioplastic, because it's made of chitosan, there's all the machinery inside the sea to degrade it and put it and give it back into the ocean as nutrients for the animals and for the plants around. So that's what we're trying to do. And this is where the biodegradability is so critical, as you mentioned, because this time, if you make a cup and you have a risk that it goes in the environment, it will degrade faster than a classic plastic today. So that's a plus.
Now, the cup that you would make out of a plastic derived from chitosan, is it as functional as polyester or polycarbonate material?
That's a very good point. So right now it's not. I'll be absolutely clear with you. We've not figured out that part yet, and we're working on this. This is an important piece in order for this to make any sense. But so right now our chitosan is not as functional as it is. But what is new with our chitosan is that the way we made it, we're able to make a chitosan that's not going to dissolve into water. So this is the first step into making something where you can make a cup, because the chitosans that are typically made, they're going to be dissolved in water, which means that when you pour water or coffee in a cup, it's all going to melt away, right? So our chitosan does not do that. The chitosan is going to hold its shape. So now what we need to do is all the research to figure out how to turn this into a material that will have the same functionalities, or at least comparable functionalities, so that it could really make a cup you can use for your tea tomorrow. And there's more research that's needed along those lines, absolutely. We're not quite there yet. But at least having a chitosan that's not soluble in water, which is the novelty that we have in our process, that's really cool, and people are excited about this.
Of course, money is always, a player in this. I remember back in, I think it was in 2011, I wrote a very optimistic article about succinic acid, which is a very important chemical. It's used to make plastics. It's used to make cosmetics. It's multi-million dollar industry. And there was a company at that time that found a way to make it, quote, green by using a genetically engineered microbe that would feed on glucose and make succinic acid. And they got the Presidential Green Chemistry Award at that time for this. I wrote a very optimistic article about that. And then I just found out recently that the company went bankrupt.
Yeah, absolutely.
Because the price of oil dropped, so that they could not compete with a product that was essentially greener, more friendly to the environment, but because it turned out to be more expensive than plastics derived from oil, it couldn't succeed.
Yeah, and that's so I know exactly about the story, and we actually reviewed that case in my green chemistry class in the last couple of years, because it's a sad story, but it's one that we need to be aware of as green chemists. So in general, molecules made from plant biomass today we have an issue with the price. And in some cases, we have an issue as well with competition with food and also with their intrinsic greenness. So what green chemistry has been doing in the last 10 years, I would say, is to really try to be a lot more systematic about the analysis it makes. And in particular, try to have metrics, meaning quantifying really how much greener it is from whatever is existing. And what we find when we do this is that making a piece of material from from biomass can be better, for instance, from the perspective of the emission of CO2, carbon dioxide that goes to global warming. But on the other end, it comes at the cost, another environmental cost, because you need to grow that plant that you're going to take it from. So you mentioned succinic acid, it comes from sugar. So you need to grow sugarcane or corn that you're going to then harvest and turn into refined sugar and then feed your bugs so that they will turn it into succinic acid. And it turns out that there's a big environmental cost to this. You know, you need to power your tractor with oil and you have emissions coming from that. You need to use fertilizers that are going to also cause runoff pollutions and also acidification of the ocean. So when you put everything together, there are a number of biomass-based developments that actually don't make so much sense from an environmental standpoint. So we're coming up with realization of this as well in the community, and this is shifting the discourse as well in many ways, because it's great to develop these new processes, but we really need to go back at some point and go on the chalkboard and really measure to see which one is really going to be better.
So when you do a so-called cradle-to-grave analysis, it often comes out different than the emotional, interpretation of what is happening. And I know that one of the focuses of green chemistry is on solvents, because we use a lot of solvents, in all kinds of chemical syntheses. We use solvents to degrease metals, for example, on a very, very large scale. And the question is, how do we green this process?
Yeah.
And so let's get Ada in here for a moment, because she works in the lab all the time using solvents all the time. And I'll be honest, when I was in grad school, which was a couple of years ago, we would use acetone to wash our glassware and dump it down the drain. We used to run chromatography columns with benzene, not in the fume hood. I mean, certainly things have changed. So Ada, I mean, practically speaking now in the lab, how do you handle solvents? Or you think you're being green with them?
So we don't flush nearly as many things down the sink as you used to. Although there are still certain solvents that, even surprisingly so, can be disposed of safely because they react with water to form safe molecules. But actually, we've got a pretty good recycling and green program at McGill to safely dispose of chemicals, specifically acetone as well. They're able to clean and reuse. But McGill is also lucky enough to have Tomislav Frischek, who is kind of pioneering in many ways mechanochemistry, which is solvent-free chemistry, which, 50 years ago, we had no idea that you could take two solids, smush them together and have a reaction happen. That's like taking my keys in a cup and saying, okay, now react. And it seems impossible, but it works. And so it's really interesting. McGill does seem to show a really strong focus in multiple ways, obviously with Audrey Moores' research, but even beyond that, with looking into green chemistry.
And Jonathan, when you worked in a lab, I mean, you did a lot of serious work in the lab, doing all kinds of DNA analysis, RNA analysis. How much emphasis was there in those days on being green?
Not a lot. I do remember working with a fellow student who was very gung-ho about environmentalism and thinking about those things, but there wasn't much. One thing that I do remember, though, was ethidium bromide. So ethidium bromide is a molecule that certainly when I was working in the labs was being used quite a bit. What it does is that when you want to separate DNA products, you usually use these gels, either agarose gels or polyacrylamide gels. And it's a little bit like a Jell-O slab. and you apply some electrical current, and it's going to move depending on how big the molecule is. You get an idea of its size. But in order to visualize it, because that DNA, you can't really see it in this jello slab, you need to throw a molecule at it. That molecule was usually ephthydium bromide. The problem is that it's a potential carcinogen. And so it wasn't, we were always very careful about disposing of it correctly. And when I was doing these things, newer molecules came on the market to replace ephthydium bromide that were meant to be greener. So you can still visualize your bands on a gel without using this carcinogen. And I'm very curious, because I haven't been in a lab in quite a few years. I'm curious to see what the uptake of these ephthydium bromide alternatives has been in the ensuing years, because a lot of these things, you have these researchers, and they're used to this product, this ephthydium bromide. They know that it works. And I think this momentum can be hard to break, right? With newer products that may not be quite as good. Maybe they're a bit more expensive, but they're better for the environment.
For what it's worth, to visualize our gels, we just put them under a UV light, so we don't have to add anything.
Yeah, but you have to have a molecule that reacts to the UV light.
Yeah.
Audrey.
Yeah, so just I wanted to add to this. I mean, this question of solvent is super interesting, and I think it really was one of the success stories in green chemistry for the last 15, 20 years. The pharma company in particular came together and actually started to change their ways and come up with guides to replace the most harmful solvents with greener ones and less toxic ones. And it's really led to, I think, a really big transformation in the field. And you mentioned benzene. Actually, I maybe I'm really old, but I remember the days when some people were talking about using them in the lab as well. I didn't do it myself, but it was still done in my PhD time. So this is over now, and I think you can see the progress in that sense. And that has been really largely borne by the green chemistry movement, because they really were big on solvent at the beginning.
Luckily, I used benzene before it was toxic.
Sure. I had a question, actually. I was wondering if the umbrella of green chemistry or sustainable chemistry also applied to the disposables that are used in the lab, because that's also a big issue. I remember, again, you're using all these plastic pipette tips, for example, or these serological pipettes. They're often single use. If you're dealing with DNA, RNA, you don't want to contaminate your stuff. So are there ways to reduce their consumption in labs now in 2021?
So I know that there are, and this has been a lot, graduate student-based initiatives that are looking into trying to help with that and trying to clean these kinds of waste and recycle them, as opposed to just disposing them as chemical waste. So there are initiatives to do this, and I can one place where they're really big with these kinds of things is in Toronto. So they have a big green chemistry student-based initiative in Toronto, where they are coming up with solutions along these lines.
Well, you know what is becoming a real big issue is the disposal of masks and the syringes that are being used. I mean, just think about that. We're talking about, just in North America, vaccinating over 300 million people. That's 300 million disposable syringes, plus all the other equipment that goes with it.
Well, that's if it's a single-dose vaccine.
What?
That's a single-dose vaccine.
That's right.
Double it, right?
Yeah. And all the masks. I mean, you just walk on the street now, and you see masks all over the place. So this is becoming a very big concern.
And this is a great example of what you were mentioning, Joe, earlier, about this thing between performance versus disposability or degradability. So, we use this mice and we want them to have these particular specs so that they will, filter certain kinds of aerosols with certain sizes and so on. But then if they go in the streets, you want them to degrade. Well, turns out today, I don't think anyone has figured out how to do both these two things with good performances. So this is, research where people can look into, because it's really needed. We see it, absolutely.
Absolutely. And that's a very interesting example, because let's go back to the time a few months ago when the whole debate about wearing masks started and which mask to wear. The challenge was finding a mask that worked well. right? That would filter out the droplets, hopefully filter out the virus, and it was tied around the face, right? So you take a look to see what materials can you use in order to accomplish this purpose. You don't think at that time about what may happen to that material after you've used it. That's a secondary thought, because first you have a problem, you try to solve the problem. Almost always that solution introduces another problem, hopefully a smaller one, that you then try to solve. So this is very similar to what we've seen over the years with various chemicals. You first introduce it, you solve a problem, and then we realize that there are issues to deal with here, just like we are now finding this. I mean, there was this terrible picture, I guess, that, I mean, everyone has seen on the internet, of a discarded glove with a fish that swam into one of the fingers of the glove. Oh. Yeah, I mean, these are heart-wrenching. And of course, you know, we've seen the pictures of the turtle with the straw up its nose, and these aerial pictures of the plastic garbage patch in the Pacific Ocean. And these are things that obviously we need to deal with. But, you know, I always like to remind people that plastic bag or that plastic bottle did not jump out of someone's hand into the ocean. It's, you know, it's not being careful enough about disposal. So we have,
and that's why as well, I mean, a lot of the green chemistry these days are actually turning into interdisciplinary research to do exactly what you say. Okay, we can make, you know, a bunch of different materials with a bunch of different properties, but what are people going to really use, in what context, what are going to be the consequences of bad use, and what are people likely to do with that, and how can we teach them to better use what they have around them, so that we can better fit the function or the functions to the actual usage, so that we can actually be better at capturing these kinds of things. So this is also something where behavioral science and psychology are becoming really important in the design of materials, so that we're much better at targeting these things. I think what you say about also going first with the intended application and solving the problem, and then second with the consequences, that is the way it happens. I think what the public is asking us more and more to do is to be much faster at, okay, we have an application, we have figured out how to do this, now let's actually look at the bad consequences that we can already know of, and try to tackle them much faster, so that we don't end up with legacy problems and take years, sometimes decades, to turn around and say, okay, we can't do this, you know?
Yeah, hindsight, as we say, is always 20/20, but we also learn from hindsight. Sure. You know, we learn from mistakes that were made, and we're always saddled with the problem in science that no matter what you do, you cannot predict all consequences of one's actions, right? I mean, who could have ever guessed back in the 1930s, when refrigerators were using sulfur dioxide and ammonia as the refrigerant, highly toxic if there was a leak, when we replaced them with freons? That was a great breakthrough, because freons are inert. The equipment worked better. There was no toxicity if there was a leak. Who could have predicted in the 1930s that 50 years later, those freons would end up in the upper atmosphere, wreaking havoc with the ozone layer? I mean, you could never even thought of that. But now that we know that history, we know to think of things like that as we go forward. So, you know, science is sort of a self-correcting discipline. And we always get better at what we're doing, but obviously far from perfect.
Like a healing polymer.
Yes, well, tell us about the healing polymer.
Yeah, so I mean, we've been, one other thing that we can do with chitosan is actually use application, and in particular for wound healing or wound dressings, and we're doing great research on this at the moment. So actually this is very new, and I can't talk about a lot of things around this, but we're really trying to develop things in this area as well, because it turns out that we need to have better ways to heal wounds. I mean, that's obvious, and being able to use a waste material from biomass would be really important. coming back to the conversation we had earlier, making it can require a lot of resources, whether this is oil, growing a plant. But if you can use some that is going to be discarded, that's a bonus. And this is where you get the best life cycle assessment, because this is a material that is not a burden in itself, other than if you leave it as it is. So you can turn it into something useful. So we're really looking into making some in this area with a great researcher at McGill, actually, Jan Lee, who's a fabulous bioengineer in this field.
So let me get a little personal with you, Audrey. You didn't start out when you were a young girl saying, I want to become a green chemist, right? So what was your path? What did you start out with, and how did you end up where you are?
So my story is really crazy. So I was years old. I was at school, and it was the year when we were first introduced to chemistry back in France, where I'm coming from. And the teacher did this really disgusting chemical transformation. He took, actually, it was a mechanochemical transformation that he made. That was really interesting. He took iron powder and sulfur powder, so two powders, which you can mix, and these will react together. It's a very well-known ancient mechanochemical transformation where it makes iron sulfide. And then you can take this powder that's been created and you can dissolve it into a test tube with HCl. So it's a strong mineral acid, and it forms this absolutely disgusting gray-looking bubbly solution that smells like rotten egg, because it elutes the hydrogen sulfide, which is the smell of rotten egg, literally. And to go around the lab and show this test tube. So this transformation, by the way, would not be allowed in a classroom without a fume hood anymore today. That's impossible. And I was the only one who raised my hand, and I walked around. I paraded around the classroom showcasing this disgusting reaction. And that day, I don't know, something clicked. I said, I want to do this for my life. Chemistry is so much fun. And then it's so of course I went on. I went to college. I did my PhD in chemistry. I always was attracted to experimental chemistry, but very rapidly I met people who enlightened me about this question of also doing good chemistry, trying to figure out how we could do chemistry, but for problems that we have today. So how do we achieve function, but also at the same time try to be a bit more respectful to the environment or of the human health? And that's how I got into green chemistry, in particular during my postdoc that I did in the US with Bob Crabtree, who's a fabulous green chemist.
So it all started with the odor of rotten eggs.
Yeah, I must say, this is weird.
Right. You never know where, one's life path is going to take you. As you sort of never end up where you think you're going to end up. It's a very circuitous route. Right, Ada? You don't know where you're going to end up.
I still don't know, so could be anywhere.
I was wondering, are there chemists who oppose green chemistry? Is this like just a consensus that, yes, we're all moving in this direction? Are there people who are saying, no, I disagree with this?
So it's interesting. I was at a conference a few years back with a really big name in the field of organometallics chemistry, who arguably has made great progress for better chemistries with the things it developed. And he was invited as a special guest to a green chemistry event, a conference. And the first words he said were, "You'll never find the term green in any of my paper, except one day I made a green chemical. So I wrote down green, for the color of the chemical." Opposed to the idea of being identified with green chemistry, it has been perceived originally as being to downgrade the pure vision that they had of science in a way. So some people have felt
like
offended that they would be greener chemistry. So it means that there are chemistries that are worse or bad. And I think it's mostly because today, if you want to have some funding, you need to go out there and write grants where you explain also how what you're going to do is going to make sure. The question of climate change is very big, so people cannot ignore these things anymore. So even people who were very uptight with the idea of never been identified with this, they're doing chemistry that's relevant to that. So they are writing the proposals, their grants by saying, I'm gonna make the earth a better place. So I think this tension is mostly gone now in the community, and people are sort of coming together. And another thing I'd add is that, similar, we don't know what's going to happen in the future. There's some discoveries that were made on pretty bad toxic chemicals that are useful in order to reactivity, and that even green chemists can use later down the road to improve a process that is. So I don't see a dichotomy here or always a contradiction,
Jonathan, in our business, do we ever come across anything that someone doesn't oppose?
No, I mean, but that's why I was asking the question. But as you said, Professor, when your grants are dependent on you wrapping your brain around a particular, way that things are going, it certainly encourages professors to think twice about their opposition to this newfangled thing.
Well, we're almost out of time here, but there's one last topic that maybe we can address, and that's the concept of greenwashing, where companies play the green game without actually being green. So do you come across that?
Yeah, so that's a big issue, and certainly, so you have chemists who are greenwashing their science. So I'm an editor to a journal called ACS Sustainable Chemistry and Engineering, and I read papers, and not to send them to reviewers, and happens that people are trying to sell pretty bad as green, with some, and what we're trying to do in this journal is to really incentivize and not really force people to come up with metrics. As I was saying this a bit earlier on the show, trying to say, can you measure it? How much solvent do you use? How much starting material do you use? Waste do you generate with this process? So that when you tell me it's going to be greener, I actually have a number to evaluate that for real. So we're really having this push to try to put a number on something. So one example that is really big, you mentioned the cradle to grave analysis that people do. So this is an idea of taking your process and measuring how much CO2 emissions are going to come from that process. So this is something that is becoming more and more standard, including inside the industry. We're trying to do this now across the board and really trying to have this idea of measuring things as well for chemistry itself in science. And I think that's hopefully going to help a lot with this greenwashing.
Well, one thing that, we've noticed companies do, of course, use the term natural in an inappropriate way, and suggest that if something comes from a natural source, it's therefore green, And one that just drives me up the wall is what they're doing now with sodium lauryl sulfate, which is probably the most widely used surfactant in the world. And now the advertising suggests it comes from a natural source. Yes, well, the original material is coconut oil, but there's a hell of a lot of processing that goes into that,
Yeah.
in order to convert coconut oil to sodium lauryl sulfate. I mean, first you got to hydrolyze the triglyceride, then you take the acid, you reduce it to the alcohol, and then you sulfate the alcohol, then you neutralize that. I mean, there's a huge chemical industry, and the fact that it happens to come from coconut oil is really incidental.
Are you telling us that when you open the coconut, it's not full of detergent that you just package and ship out?
Exactly.
I have a great example. So it used to be in the 50s, 60s, 70s that most of the vanillin that was produced was actually coming from lignin, which is coming from biomass, from wood. But the process to make the kind of lignin that could lead to vanillin was absolutely gross. So there was this place in Ontario where there were making paper and generating this lignin via this process. But it was so polluted that they had to shut down this plant. And what replaced it was actually vanillin from oil, because it was far less damaging to the environment to do it this way. And it's only now that we're coming back the loop and trying to make vanillin from other sources by essentially enzymatic process now, from rice bran, I believe. But you see how, we always go back in circles. I mean, it used to be made from lignin, but it was discarded because actually it was so disgusting to the environment that it didn't make sense.
One of our great nemesis is this woman who calls herself the food babe. She has a large following on the internet. Well, according to her, vanillin comes from beavers, and it comes from the poop of beavers, or so she suggests, which is, of course, total nonsense. But what she's confused is the substance called castoreum, which beavers produce. And there have been some publications using that as a starting material, and you could convert it to vanillin. But that's so what? That's an academic interest. Nobody in the world is making vanillin from beaver extract. But she goes on online and she tells people that that when you're having vanilla ice cream, you're eating beaver anal extract. This scares people. And, this is where, she takes 2 + 2 and makes 5 out of it. And this is what we deal with all the time, this kind of nonsense. But we were just saying before, we haven't heard all that much from our friend, the food babe, recently. She's quieted down during these COVID times.
So I would like to know how many people are actually right now running after beavers in order to extract this thing from them, to make all the ice cream that everybody's eating. I mean, just the thought of it is mind-boggling.
It would take a lot of beaver extract.
Ben and Jerry's apparently have this huge beaver farm. That's what I've been told, anyway, through the grapevine.
I have.
Okay. Yes. Ada.
Just quickly before we go, I'm wondering if with plastics or materials of any kind made out of chitin, if there's any risk of allergy for people that are allergic to shellfish.
So that absolutely, that's a great point, and especially as I was discussing as well, biomedical applications. So chitosan is used today in biomedical applications routinely. There's a number of products that are sold and used in for surgeries, for all sorts of biomedical things. And the way you do this is that in the process, you have a specific step that is going to remove the protein. And what we're doing right now is checking that our process does the same thing. So in all the measurements that we've made, we can't see any protein. The protein seems to be completely gone. But what I'm doing right now is chasing a partner that I have in the industry to really give me the exact measurements that they do in the industry, the exact standard, so that we could absolutely check for sure. But we're very attentive to this, because you're right that this is a big thing. We don't want to start to make plastics, let alone wound healing devices or materials that would actually give an allergy to people. That's really not what you want to do.
Thank you. Well, that's it. We're out of time. And that was a fascinating discussion. And our listeners, I think, learned a lot about what green chemistry is all about. So thank you very much. I was Professor Audrey Moores here at McGill, and she is an expert in green chemistry. You can check her out. All you have to do is Google her name, and you'll get hundreds and hundreds of hits. So thanks, Audrey. Thanks very much for joining us. Thanks to Jonathan. Thanks to Ada. And also thanks to Stuart, who puts all of this together. And we will see you all in 2 weeks' time. Bye.